Hello dear students, my name is Vishal Arun Naik. I am working as an assistant professor in Department of Chemistry, MPSC College Panvel. So our today's video's topic that is from analytical chemistry, and the topic name is optical methods. In that optical methods, we are going to study first instrument, that is flame emission spectrometer. Okay, in that flame emission spectrometer, we discuss or we focused on that is the principle and instrumentation of flame emission spectrometer, then applications of this flame emission spectrometer and the limitations of this flame emission spectrometer. So let's start to our today's video. So what is the basic principle of flame emission spectrophotometer or flame photometry? So generally, when any particular substance, most of this flame emission spectrometer is used to detect the concentration of metal ions present in different samples. So when we particularly heat that sample, the electrons from that sample or that metal ion goes from ground state to excited state by absorbing the energy that comes from heat. Okay, after that, that molecule comes to the ground state by emitting some amount of radiation. So in flame emission spectrometry, we detect or we study that emitted radiation. So always remember that in a flame emission spectroscopy, we focused on the emitted radiation. So that is the basic principle of flame emission spectroscopy. So what happened in flame emission spectrophotometer? So I have written something here that when a solution that is containing a metallic salt is aspirated in a flame, first what happens, that sample or the water present in that sample, that is evaporated, because we actually introduce the aqueous solution. So aqueous solution means it contains water. So in the first step, when that water or when that sample injected into that flame, okay, water get evaporated and we get a solid particles of metal salt. So solid particles of metals are there, okay, which are remain in that particular part. Then after absorption of high amount of energy, that molecules again vaporize itself, okay, and get converted into and dissociated into M and X. So this metal salt, suppose this is an NaCl, sodium chloride. So when vaporization of sodium chloride takes place, we get Na plus ions and Cl minus ions, okay, in a dissociate form, that is in a gaseous atoms. Then atomization takes place by absorbing another amount of energy, that is higher amount of energy, and that molecule splits into metal and non-metal in a gaseous state. So that is the atom in a ground state. And after that, when that heat contains a high amount of energy. So after that all molecules get converted into that ground state, atoms get converted into an excited atom by absorbing energy. So that excited energy is indicated by star. Okay, so in this case only metal get absorb energy. Why? Because metal contains some amount of electrons. So electronic transition takes place from ground state to excited state, and molecule amount that energy and get excited. And after some time, that molecule, particular energy, each molecule has its own characteristic wavelength, that particular molecule absorbs that wavelength only. Okay, and emission and absorption radiation is similar of that particular metal ion. So that particular, after some time, that particular metal ion emit that energy, that is indicated in form of H mu, and that metal ion comes from excited state to ground state. So in the flame emission spectrometer, that energy is studied or that energy is determined by using this instrument. Okay, so that's why we determine what amount of metal ion present in that particular sample solution. So this is the basic principle of flame emission spectroscopy. So Boltzmann equation particularly used to calculate what amount of excited atoms are present in that particular sample solution. So this is a general formula, that Boltzmann formula, which is used to calculate what is the concentration of that particular substance. Okay, so this is the basic principle. The next point, that is the instrumentation of flame emission spectrophotometer. So as we see in this diagram, so first part, so particular the components of flame photometer, I have written something here, that is burner. First is a burner. Okay, burner are of two types, total consumption burner and premix burner. okay, where our sample get heated, okay, and they emit radiation, okay. So this is the first part, that is called as an atomizer. So sample sucks from here, fuel and oxidant is used to burn a flame. That emitted radiation has its characteristic wavelength reflected by this mirror plane, okay. Then that goes towards the monochromator. We use different types of monochromator. We use prism or grating prism or quartz as a monochromator. Then that monochromator, what is the role of monochromator? Monochromator convert, or monochromator only allows to pass an individual wavelength with a high characteristic, are only pass through this monochromator, through this slit, and then photomultiplier tube multiplies that signal, okay, and amplifier amplifies it, and detector readout actually read that. So photomultiplier tube is used to convert that light energy into an electric signal. So this is the instrument, that is include different parts, that is the instrumentation of flame photometer. So one by one we discuss on that particular parts. So this is the most important point, that is the preparation of sample solution. So for using flame emission spectrometer, first of all we have to prepare a sample solution. Okay, so sample solution is prepared in a water by using a different concept or different methods. Once that sample is prepared, that it sucks from this tube, okay, and this is called an atomizer. Atomizer means what? That particular atomizer converts the sample solution into smaller droplets, tiny droplets, so which are easily burned in a flame. That's why atomizer is attached here, which sucks the molecule and spray the molecule or convert into tiny droplets which are sprayed in a flame, so that particular sample easily burn into that flame. So that's why we use an atomizer in a flame emission spectrophotometer. So which type of burners we used in a flame photometer? This is the most important part of flame emission spectrophotometer. Okay, so two types of burners we generally use, that is total consumption burner and premix burner. So this one is a total consumption burner. As the name suggested, that total consumption means total sample which is present in our particular sample container is absorbed into this and aspirated into a flame. That's why it is called a total consumption burner. So in this diagram we actually seen that there are three concentric tubes from which one fuel is introduced and oxidant is introduced, which actually burns the flame. Then sample, that is attached to the atomizer, sucks from here and aspirated into a flame. So maximum amount of sample get introduced or maximum amount of sample get aspirated into a flame. That's why it is called a total consumption burner. Okay, and what are the advantages of this burner? That entire sample is introduced into a flame, so it is more sensitive. Then the flame can be adjusted to produce the high temperature. As we know, metal ion has a higher temperature, higher melting points. That's why that burner produces higher temperature. So metals easily get converted from ground state to excited state and electrons get absorbed by it. Okay, so this is the important point of burner. Then there are some advantages. So as total sample get absorbed or total sample get aspirated into a flame, so our flame is noisy, okay, and turbulent flame is there because more amount of sample gets introduced at a time. That's why our flame is turbulent. Okay, so this is the first type of burner. Then second type of burner, that is the premix burner. Premix burner, as the name suggests, premix, or it is also called as a laminar flow burner. Premix. So in this case, fuel, sample and oxidant first mixed here, okay, and using baffles, okay, using baffles, that particular sample along with fuel and our oxidant filter out here by using these baffles and then introduce into a flame. Okay, so only small amount of sample is introduced. Why small amount of sample is introduced? Because these baffles actually used as a filter. So smaller particles of the samples get introduced into a flame by these baffles, and maximum amount of sample get drained out. So only 5% sample is introduced into the flame. Okay, so that's why it is called as a premix burner. Okay, before mixing, that's why it is called as a premix burner. So what are the advantages of the premix burner? So the flame produced is stable. Why? Because the sample introduced into a flame which is very much smaller in quantity. So stable flame is there. Vaporization, atomization and excitation takes place very efficiently because sample is introduced very smaller in size, and there is only 5% sample get introduced. Then it is sensitive and reproducible results. There are some disadvantages. Only a small portion of the sample reaches to the flame. So results were not at that much as accurate as total consumption burner. So due to large wastage, fewer atoms are excited. So we cannot get a 100% accurate result in this case, and the sensitivity is lower for the estimation as compared to total consumption burner. So these are the two general burners which are used in our flame emission spectrophotometer. Then next point that we have to study in flame emission spectrometer, that is the application. So there are two types of applications are there. First is qualitative application and second is quantitative application. So here qualitative application, that is also called the identification of element. So the metal ions which are present in a different form of a sample or different samples get determined by using FES. So which are those samples? So sodium, potassium, calcium, magnesium present in the soil are also determined by using this flame emission spectrophotometer. Then fertilizers. We know that fertilizers contain NPK, that is potassium, sodium, calcium, magnesium, different types of metal ions present in a fertilizer also determined by using flame emission spectrometer. Then biological fluid contain different type of elements are also determined. Biological fluid means blood samples, urine samples and other samples are contain different type of metals which can be determined by using flame emission spectrometer. Then lead, if lead present in a petrol or cement containing calcium, magnesium. So in cement industries, petrol industries, oil industries, we use flame emission spectrometer for determination of the metal ions. Then glass analysis, that is the purity of glass also determined by using this one. And then organic compounds, boron, physiological and clinical studies, we use flame emission spectrometer post-oxide. So there are wide applications for the identification of metal ion of this FES. Then next application, that is the quantitative analysis. So particularly this instrument gives the not just in a quality, we also determine the quantity of the sample or the metal ion present in the sample. Okay, so there are three different methods which we use to determine the quantity of the sample. So first is the calibration curve method. So this is in a graph. So what is the calibration curve method? So we have to prepare a series of standard solution, and one by one we aspirated that series of sample solution into an flame and determine the emission intensity of particular substance. So as we know, the standard solution means the solution whose concentration is known. Okay, suppose I have to determine that is the copper. Okay, so we have to prepare a standard solution of copper. Okay, then after aspirating sample solutions, burn our sample solution which is in metal ions which present in that sample solution, we have to determine, so which is aspirated in a flame emission spectrometer. After aspirated into that, we get emission intensity, and by using that emission intensity, so by using a standard solutions, we prepare this graph, and then our sample contain particular amount of emission intensity. So by using that emission intensity and by using this graph, we determine what is the concentration of unknown solution is there. So this is a very simple method which is used in the instrument or which is used in the software of that instrument. So this is the widely used that is method for the quantitative analysis of any kind. That is in AS also we use this method. So this is the calibration curve method. Then next method, that is the standard addition method. So in this method, emission intensity of unknown solution is found by aspirating into a flame. Then a series of standard solution in which that is the unknown amount, unknown x remain constant. So as we seen in this graph, x, the amount of x is remain same. That is our unknown sample solution. And the standard solution that is we are preparing, we add that standard solution in a different amount. In the first one, we not adding some standard solution that is a 0 amount. Suppose in second one, we add 1 ml. In third one, that is 2, 3, 4 and 5. So the unknown sample solution, the quantity remains same, X remains same, but the quantity of standard is varying. Okay, so one by one we aspirated that all the samples in a flame emission spectrometer. Then we plot this graph against emission intensity and concentration of standard and concentration of unknown. We get this type of a graph, and if we extra plot that graph on another side, on this side, we get our concentration of our unknown sample solution. So this is called as a standard addition method, because varying amount we add standard solution to that. And the last method of quantitative analysis, that is the internal standard method. Okay, a series also, in this method also, a series of standard solution containing the same element is present. We have to prepare that. Then the fixed amount of a suitable internal standard. It is same as the standard addition method, but internal standard is quite purified as compared to standard solution. So internal standard solution is then added into each of standard solutions, then blank, and then sample solution. So all samples which are we prepared, standard solution, blank, and our sample solution, we have to add an internal solution, internal standard solution into that. Then one by one we aspirated that into a flame, and we determine or we get emission intensities. Okay, so we get emission intensity of the analyte and the emission intensity of the internal standard. So by taking the ratio of that one, and we plot against the standard solution which we prepared. Okay, and by using that we also get the concentration of unknown solution. So these are the three general methods to determine the quantity present in the sample solution. Okay, and the last point of our today's video, that is the limitations of flame emission spectrometer. Every instrument has its own limitation. Okay, so flame emission has some quite limitations. So first limitation, that is gives the total metal content in the sample, but does not give any information about the molecular condition of the metal. It actually gives which metal ion is present in our sample solution, but what is the condition of that metal ion, whether that is oxide, whether that is sulfide, chloride, or any other. It does not give any information regarding the molecular condition of the metal. Then it cannot be used for the detection of all metals. Only group 1 and group 2 are roughly detected. Okay, then only liquid sample get introduced into a flame emission spectrometer. We cannot analyze the gaseous sample and solid samples directly into flame emission. Only liquid samples are determined. And the most important limitation is that interference by the same element, or interference by the element with the same wavelength. If two elements have the same wavelength, okay, so determination will be wrong, or the quantitative analysis becomes wrong, because if two elements are present, it becomes analyzed as only a single element. Okay, so the magnesium and iron, if we have to determine the magnesium and iron, okay, so if magnesium is present, it detected as an ion. Okay, and if we have to determine the iron and magnesium is present, so it determined as a single. So this is the interference which is produced in a flame emission spectrometer. And the last limitation, that is the elements with low ionization potential not estimated correctly. Today we actually discussed the instrumentation part and the types of burners in flame emission spectrometer. Then applications of flame emission spectrometer, generally applications are quantitative and qualitative. Okay, and the limitations of flame emission spectrometer. So we stop our today's video. Thank you so much.